Hello everyone. So this is a video solution to the questions in tutorial 6 document. So in tutorial 6 document, originally I included three of these questions, but later I found out within the question 1 there's some problem with question 1. So I have removed question 1. So now I have changed the question 2 here as question 1. Okay, so in this video, just going to give you solutions for question 1. So if I already go through the tutorial 5 document, basically, hopefully, and then you will get all the necessary skills on of how you're going to use a steam table to find the properties for the water and the steam. And in this tutorial 6, we're going to, so you can see that although we have two questions here, so these two questions will be a little bit more complicated. So basically, we're not just going to learn how to find out the steam, how to find the properties from using steam table, and also we're going to apply some other theory, such as the first law of thermodynamics, something like that, and then to do especially for some applications. So for the first question, if I have a look at, it says a rigid tank. So whenever we read a question, there actually quite a lot of information inside this question. So first of all, if we have a look at anything about a rigid tank, this means that this is a closed system, okay? Because rigid tank has no opening. If there's no opening, and also you can see that the mass is fixed, 4.5 kilogram is fixed. So rigid tank means that this is a constant volume process, because the volume of a rigid tank will not change during any process. So this basically means just as if it's a constant. So it's constant volume process. Okay, so any process inside that rigid tank is a constant volume process. And this is a mass given, so that's the mass of the water. Okay, so be careful here. This is water. Okay, so sometimes it can be gas and sometimes water. So once the working fluid is water, we need to think about, we probably need that steam table to find out all the properties relevant to the water. Here in the saturated vapor state, okay, so this is a very important information here, okay, because it states that what kind of a phase is water under this, under this initial condition, because it's saturated vapor, and we know that this saturated vapor term is only used for the state, okay. If you think about that platform, you remember that platform. So on the left-hand side, the starting point is what we call the saturated water, and we give a subscript F for saturated water. And for the right-hand side, right-hand end, okay, on that platform, we give it exactly the saturated vapor state, and we use a G, okay, a G, the subscript G, to identify any state which is a saturated vapor state. So it is at a pressure of 40 bar, and heat is transferred from the system to the surroundings, okay, so that it cools down. So basically this is a cooling process, so we're talking about the process here, to the wet vapor. Again, this is a very important information. It shows that the end state of that, by the end of that process, the state and the water, the phase of the water has changed to wet vapor. Okay, wet vapor. Think about what kind of equation I'm going to use to describe the wet vapor. And now the pressure reduces to 10 bar. So we have two pressure here. Okay, since this is a process, we can just write that P2. Okay, just end state P2, and the 40 bar is P1, 40 bar here. Okay, so now we need to determine, first of all, the volume of the tank in cubic meter. So we're talking about V, capital V. Okay, then we need to find out all the information regarding the volume, such as the specific volume. Okay, so let's do the first one. So the first one, as I said, if we want to calculate the volume of that tank, the volume of the tank, V, okay, so this is defined as m times the specific volume V1. Okay, and then we need to find out the V1, so the initial condition, and we need to find out at the initial condition what the status or what phase of that water. So obviously here we found that initially the water is in a saturated vapor state, G. So this means that V1 is equal to Vg, okay, because V1 is not a wet vapor yet, it's a saturated vapor state. So we'll give it a subscript of G, Vg here. And this will be found specifically at a pressure of 40 bar. 40 bar. Okay, so now we know the pressure and we can use the steam table. So here, okay, so we're going to use the saturated water and the steam table. So this is the pressure, okay. So now we find the 40 bar. Okay, 40 bar. So we know the third column is called Vg, right? Vg. So that's that here. So at the pressure of 40 bar, the Vg is that is 0.04977 cubic meter per kilogram. Okay, so we just need to write down that value. So this is 0.04977 cubic meter per kilogram. Okay, so this is a Vg at the 40 bar, and which is equal to V1. So we know the mass, right? We know the mass, and then we can calculate the volume, which the mass is 4.5 kilograms times that, which gives us the total volume of the tank in cubic meter, which is about 224 cubic meter. Okay, so that's for the first question. Now let's have a look at the second question. So the second question is asking us the dryness fraction of the water in the tank after cooling. So that's after cooling is also the end state of that cooling process. So we're talking about the dryness fraction, and then we have a look at that at the end state. So what's the phase of the water at the end state after? So after it's cooling down to the wet vapor. So we know that at the end state, the phase of water is actually wet vapor. Okay, wet vapor. So the volume of the wet vapor, V2, the specific volume of wet vapor, is exactly equal to V1. This is because, as I just mentioned earlier, this is a rigid tank, so it's constant volume process, and volume will be kept at the constant. V2 is equal to V1, and then we have already calculated V1 with that 77. Okay, and at the same time, V2, okay, V2 is because at the end state, as I said, the water is in a wet steam condition, so V2 is also equal to V wet, especially at a pressure, so it's at another pressure, at a pressure of 10 bar. Okay, so we need the equation to calculate the V wet. In the formula sheet here, we have a couple of equations. So here, right, so it shows the U, how we're going to calculate the U, and the V for the wet vapor. Okay, it also has the same, very similar form here. Okay, so now if I'm going to use that as a U wet, so we have XVG, okay, XVG at 1 subtract XVF. Right, okay, so now what we can do is that at this new pressure, the end pressure 10 bar, according to the steam table, we will be able to find out the Vg and the Vf. Okay, so at 10 bar, so we just check the steam table again. So at the saturated water and the steam, we found our pressure of 10 bar, which is there, and the third column is here, 0.1944, so that's for Vg. Okay, so Vg is equal to 0.1944 cubic meter per kilogram. And how about the VF at 10 bar? Okay, as I mentioned a lot of times now, so we can't find a VF here, it's only VG there. So VF will only be found on page 10, and it's called Further Properties of Water and Steam. So you can see there, VF is there. Okay, so we need to find the pressure on the 10 bar. So we have a look. We haven't got exactly the pressure of 10 bar. We do have a very close value, which is 10.03 bar. Yeah. So we can just, as I said, it's very close. So we can just use the figure, you know, that's 0.1128. And you do need to remember, you need to times 10 to the order of 10 to the power of -2. So this is a VF at 10 bar. So we looked it up by using the steam table here. So VF is 0.1128. Remember to times 10 to the power of -2. It has got the same unit, kilogram. Okay, so now we have VF, VG, and then we actually need to calculate dryness fraction. So we don't know X, okay, but we know V2 because V2 is exactly same as V1. Okay, so that we can write on the left hand side, we can write that's 0.4977 equal to X times V times VG. Okay, X times VG. X at 1 subtract X times VF. So VF is 1128 times 10 to the power of -2. Okay, so next what you need to do is just a little bit of mathematical skills. So you need to rearrange and then to calculate X. And after the rearrange, so you can get 19, so you can double check your calculations, times X, which is equal to 0.48642, something like that. And finally you can calculate the X, the dryness fraction here, which is 0.252. Okay, so that's basically, you know, the solutions for this question. As you can see here, so it's not a very direct question asking you just use a steam table to find something for me. So you actually needed to think about what information do you really need for this particular question, and then you need to use a steam table to find, you know, the necessary information for you to do all the calculations. And in this particular question, we're talking about the volume here. Okay, so everything is about the volume here. And then we have information here, constant volume, so everything is about the volume. Then you need to use a steam table to find all the information, you know, the VF, VG at different temperature. So we need to use a steam table to find information of the specific volume. Okay, so that's a solution for question 1 in tutorial 6.